name is Meytal Baron, and as Amir said, I'm a senior industrial designer here in Aran Design Studio. And I'm going to talk about how we're integrating industrial design in your development process. And I want to do it through telling you a story of a very interesting product. It's actually a few products that we have developed here in Aran. And it's also a product of Edwards, so we have some friends from Edwards here in the crowd. I mean, okay, yes. How are you, Aran? Okay. Okay. Again, another heart valve. This is actually a replacement. This is the artificial aortic valve that's being replaced in an open heart surgery. I mean, before we were talking about a transcatheter valve replacement. This is an open heart surgery. Very nice picture, isn't it? Well, up until about 20 years ago, the only way to replace a heart valve or to treat heart valves were through an open heart surgery. Now, you probably understand from Tupilsky's lecture that open heart surgery is a very difficult procedure. I mean, it's difficult, it has a high risk, and even if nothing happens, I mean, the patient gets better, I mean, it's a very long recovery period. And up until 20 years ago, nobody thought that there could be any other way to replace a heart valve besides open heart surgery. Until this guy came along. This is Dr. Alan Kirby. He's a French cardiologist. And he was interested in finding a new method to replace a sick valve without opening the chest. And this was his idea. I think it's actually his sketches here. And his idea was to design a new valve that will work like a stent. So you can compress it, put it on a catheter, and insert it through one of the arteries into the heart. And then inside the heart, you expand it and deploy it in the right position by using a balloon, by inflating a balloon and putting it into its place. Now, that's an excellent idea. So, of course, he registered his patent, and he went out to the world and started looking for people or companies to invest and develop his idea. And these are some of the reactions that he got. Okay. Eventually, he did manage to find a few partners and raise some money, but still couldn't find a company or a design house that will help them develop this very challenging project. Until one day they came here to Israel, and in a cardiology convention in Jerusalem, they met a few people who told them, okay, why don't you go check this company in Syria, Aran. And they came to Aran, and they presented their idea to the managers, and the managers decided this is a very interesting project, very challenging, but very interesting with a high potential, and they not only decided to take the challenge and develop it, they also became small partners in the company, meaning they really believed in this idea. Okay, this is our development floor, just one floor below us. For 4 years, I mean, in Aran here, we assembled a team to work on this project for 4 years, and those people were sitting here in the building with the PVT people. PVT is the company that Alan Kirby and his partners have established, working together for 4 years on developing and getting into the first in men with the new valve, with this new procedure. Here you can see some of the models, because of course in that kind of development procedure, a development process, you must have and try and test a lot of models. So on the top, for example, you can see some of the models that were using polymeric leaflets. That was one of the things they were testing. And here you can see leaflets that are made of biological leaflets, but from tissue from animals. Eventually, these are the ones that were chosen. They gave the best results. And after 4 years, in 2002, here you can see Dr. Alan Kirby with a big winner's smile after such a long time of working and persisting on developing this project. And this is his brave volunteer, his patient, that volunteered to take the first TAVR, that's the transcatheter aortic valve replacement, the first TAVR in the world. And both of them look very happy, of course, because it was very successful. 2 years later, Edwards bought this company. But of course, as probably most of you know, developing a medical product does not end with the first in men. Afterwards, you still have quite a few years to develop the product until you really get it into the market. So I will try to do it in a nutshell, but this little movie is a bit slow. How does the TAVR procedure works? Okay, let's see. This is the heart. And we're looking into the aortic valve. You can see it doesn't open properly, it's calcified. And now what we would like to do is we want to put a guide wire through the femoral artery into the heart. Just a second. And the guide wire is used to, all the other devices run on the guide wire, but it's also quite useful because to do this procedure, you don't see the heart. You see it only through the imaging equipment. So the guide wire is metallic. It's easier you can see it through the imaging equipment. It helps guiding the physician to do the procedure. There's a balloon coming in. It expands over the valve just to stretch it, to give some room for the valve to come in. And this is the delivery system. It's coming in. It's opened. The sheath is, you see it goes through the artery, over the aortic arch. Just going over this arch is also quite a challenge. You see how it's placed into the heart. Okay, the valve is in its place. Yeah. You expand the balloon, and that's it. Automatically, the valve starts working. Now, what an improvement this is if you think about the open heart surgery we had before. So great, we have this amazing new procedure. We have this wonderful new valve. Everything is working great, but there's still something missing. Okay, how do I put this valve into the heart? It doesn't I can't just squish it with my hands, right? How do I turn this into this? And that's not the only challenge. Because we're using the animal tissue leaflets, we can't store the valve compressed. It needs to be compressed in the cath lab bedside just minutes before it enters the body. Otherwise, the leaflets and the material will be damaged and won't work properly. And of course, all of this, if we are designing such a device, think about the standards of sterility that we need. It's touching an implant, so that's the highest standards of sterility that there are. Of course, when we were developing the first valve, we needed to have some kind of device like this, otherwise we couldn't do any experiments. So of course our engineers have designed some kind of a machine. If you look at it, it's quite obvious it was done by engineers, right? And they had a really nice mechanical idea how to do it. It's some kind of a combination between the chuck of a lathe and, of course, the aperture mechanism, and combined together. And they added, of course, a few features because while working on the valve, they knew that they are needed. For example, there's a gauge on this side to check the size of the balloon, and there's a smaller gauge on the other side to check the size of the valve, and there's this very comfortable, easily, nicely touched knob that you have to twist forward and backwards and forward and backwards, and to apply this machine. So, and how do you compress the valve with this thing? First you would put the valve on the catheter, put it inside the aperture, try twisting, start twisting it back and forth, and every time you have to take it out, check it on the gauge to see that it's the right size, and back and forth until you get it. Now, of course, when you want to go into the market, you can't go in the market with a product like this. I wouldn't even call it a product. To make it into a product, or let's say a commercial product, it needs to be designed. And so this is where the design comes in. And this is the first commercial product, the first commercial Crimper, and thank you for loaning it to me for the presentation. And you can see that it has all the features from the first mechanical model. It has the gauges, like the gauge for the balloon here and the gauge for the valve, and it has the aperture here. But see, we replaced the knob, which is very cumbersome. We replaced it with a handle. Now it's much easier to use, you see? And there are a few more features. For example, you see the colors? There are a few different sizes of valves, so of course we need different colors. There's color coding for the different crimpers. And not only that, this is a disposable device. This is one of the reasons it's made out of plastic, because it needs to be as cheap as possible, because to cope with the high sterility standards that are needed for something that you use in the cath lab and touch as an implant, it needs to be, the best way to do it is just throw it after you use it, just one time. Okay, so this product went into the market, and hospitals and surgeons started to adopt this new procedure, and a few years later, Edwards came back to Aran and said, okay, now we have a lot of feedback from the market. We want to make an improved version. And this is great for us. Why? Because for developing this device, we didn't know the user needs. We just assumed that, that the needs that we determined that are needed is the ones that we assumed that are needed according to our work in the lab, in the experiments. And we didn't have any real users to tell us what they like, what they don't like, what is more comfortable for them, what is less. And now after we get the feedbacks for the market, after a few years it's been used, it's much easier for us to make a better product. So you can see a cath lab here. Usually we would go out in the field and we would check how people are using the device, and we talk to them and we see what they like and what they don't like. And look at it here. There's the surgeons here. There's the patient just lying there. You see they're working around his thighs because they're inserting through the femoral artery, the imaging system, and just over there, here you can see there's a whole table that's only dedicated for crimping the valve. And you can see this device on the table there. And the main feedback we got from the market, from the users, was that this device is a bit hard to use. Why? Because you have to apply a lot of force to crimp the valve. You actually really need to lean on it with all your weight sometimes to do it properly. So our first task with improving the first version was to improve the mechanism. And this is the model. This is a real work model that was done, I don't know how many years ago. It was done by an engineer here in Aran called Edwards. It's nice. And I think he really did a really good job, because improving the mechanism here, because look how easy it is. I can just move it with one finger. Really nice, isn't it? And another thing he wanted to add was those walls from both sides of the drum, because they support the drum from both sides, because we understood that from the amount of force that the users are putting on this device, sometimes it opens a little bit. So this is to protect and close the drum properly. So this idea, this new, this update of the design was mostly to cope with the amount of force that you need to put on it. Now I want to ask you a question. If we're talking about how much force you need to apply on some device or some machine for the user to use, is it a task you would give to the engineering department or the design department? Silence in the audience. What? Design or engineering? Okay, well, of course you're both right, because the engineers would be the ones who design the mechanism, but it will usually be the designers or the human factor experts to say how much force do you need, how much force is comfortable for the user to use, and what is the best movement for the hands or for the user to do to apply this device. Okay, so we had this model, and now what we do is we use this model as the layout, because now we're moving into the phase of the styling or the look and feel phase. So we take this and we try different kinds of styles that we can apply on this. And now if you look at it, you see that this is the layout, and all these different styles, they comply with the layout of this one. It has the drum, it has the same size of a handle, it has the two walls on both sides, it has this base. It's all the same, but look how many different styles you can make. And this is just the top 3 that were chosen to present to the client, because usually before getting to these nice 3D rendering images, we have a whole wall full of hand sketches and ideas that we do. And the idea is to show a few different styles for the client to choose from, of course, according to what they like, what they don't like. It needs to match their branding. They want it to resemble or not resemble a medical product or whatever they choose. And from these three different styles, they chose this one. So now I'm going to show you the second version of the Crimper. There it is. Okay, and for the people in the back, bigger image there. Now, this was a big improvement, not only because of the mechanism, but also because of other criterias. The first version, as I mentioned before, you needed to have the whole device for each size of valve. So it means that logistically, the hospital will need to store quite a few different sizes of crimpers. The crimper is relatively large, and you need to store a few different kinds if you want to use different kinds of valves. And then when you need to go into the cath lab, you need to choose a valve, and then you need to choose the right crimper. Here, you don't need it anymore. Why? Because of, now I have to do it with one hand. Lo oved. Okay. Okay, thank you. Okay, this little piece of plastic. Now, this is it's a little piece of plastic with a lot of wisdom in it. Why? Okay, because now this crimper, it matches all the sizes of the valves. And if you want to adjust it to the right size, you just take this stopper. And each stopper has, of course, the same color coding as before. And this one can come with the box of the valve. So there's no way there's going to be a mixture between the different sizes. You always have the right size. So what do you do with that? You click it here, okay? You open it, you put your valve and your valve inside, and then you go once. It stops you exactly in the right location. You open it again, you can see that the valve is okay. You take it out, and then you close it again. And then, you see, there are no gauges anymore. You don't need them, because right now, with this little piece of plastic, we know that we have the right size. So it actually really improves the workflow. You don't have to take it out all the time and check it all the time. So the user knows that he's done his job properly and according to what they need. Okay, we finalized the design. We made a few models. We tested them. We like what we have. And now the next step takes and again, the engineering is taking the lead, and they're doing the phase of design for manufacturing. Now, of course, there are a lot of things you need to think about where you're doing the design for manufacturing. The first is, I mean, we said this is going to be, it needs to be rigid enough, so you can see all the ribs that they added here, and you see all the parts. It needs to be assembled easily and without any mistake. And very importantly also, since it's a disposable product, it needs to be designed for cost. So it needs to be strong enough, so you want to add some plastic, but on the other hand, you want it to be cheap enough. So there's a balance between them, and so that's a challenge for our engineers. And it's very important also for us designers to be part of this phase, because we want to make sure that the engineers don't ruin our nice design while doing their work. Now, of course, I just showed you is a work process of something like 10 years together. And after designing and working together with Edwards on the different versions of the Crimper, and there's also here you can see another version. That's a newer version, and we're still working. There are still new things in the barrel for us to do. You can see the whole line. Now, since the first valve, Aran have really developed, and today we are evolving to provide a real multidiscipline design process for our clients. We have all those departments. We can offer industrial design, mechanical design, electronics and software engineering. We also really expanded our prototyping and manufacturing abilities, because that supports the process of the product development. And all of this is working together also to provide a turnkey solution that complies with the 13485 standards and the FDA design control guidelines. We are very proud in Aran to be a part of this project because it really changed the way heart valves are being replaced today. It was the first time in the world somebody done this. And if you look in the American Heart Association website, you can see under the what is TAVR, you can see the image of Edward's heart valve. It's really nice. And these are not the only people who acknowledge this achievement. It's also Israeli Post and the Israeli government. You can see they have issued this post, this stamp of Israeli achievements in cardiology. And if you are collectors, then there's a whole series of them, so you can take them. Thank you very much.